Welcome to example number 10. This is a question about a dart gun. So we have a dart gun with a given spring constant of 400 newtons per meter, which is compressed a distance of 8 centimeters away from its equilibrium. The mass of the dart is given as 20 grams, and we want to find what is known as the muzzle speed. So what is the speed that the dart leaves the spring-loaded dart gun? Okay, so as you can see, this problem involves spring potential energy, elastic spring potential energy, because there's a spring that is being compressed and then brought back to its relaxed position. Also, you can see that there's a dart that is moving off here with a velocity, and hence we must have kinetic energy. Now, fortunately in this problem, the problem is such that the dart gun is made to go horizontally only, which means that the dart is not moving um, upwards in any way, and so or downwards, and so there's no changes of gravitational potential energy. I guess this problem could be made more challenging if we were to slant, say, the dart gun off at an angle. All right, so what do you think you need to do when we solve this type of problem? What is the main concept that you should start off with? Well, hopefully you realize that we have ignored friction, which means there are no non-conservative forces, which means that this is an isolated system where we can say the energy initially is equal to the energy finally of the system. So the total mechanical energy of the system is constant. Now remember, mechanical energy is made up of kinetic energy and potential energy. So we could write that both for the final and initial states. So the next thing I do after I write conservation of energy and break up that mechanical energy into the different forms is that I'm going to start substituting in our equations here. We have 1/2 mass times velocity initial squared plus not gravitational potential energy. There's no point. You could put it in if you like. You could put mgh if you'd like. But really, it's not going to affect anything because the height initially and the height finally is the same. So I'm going to neglect putting in potential energy. I'm only going to include the potential energy that is elastic. So we have 1/2 kx initial squared. And then on the right side, we could write the same terms. 1/2 mv final squared plus 1/2 kx final squared. If you're not sure, you could always add in the mgh's and see if you have to cancel or not. Okay, so the next thing is I'm going to write down my given here. So it's always important that when you start the problem is that you draw a picture. I like to draw a picture of it before and then a picture of it afterwards. And then I label all the given information. So I can see the x initial is 8 centimeters, negative 8 centimeters to the left. The initial velocity of the dart is 0. And then finally, we can see that the spring comes back to the relaxed position, so the final displacement is 0 because it's at the relaxed position. But the dart is now moving, and hence it has kinetic energy. So we can now start to sort of cancel some terms off. So if we look at the picture before, we can see that the velocity is 0, which means that there is no kinetic energy. This term is just going to drop out. And then if we look at the picture afterwards, we can see that the spring goes back to its relaxed position, which means that there's no more spring potential energy. So therefore, this term drops out because x is 0. And so what you really have is the initial spring potential energy is all completely converted into the final kinetic energy. And so you can cancel some things off. You can see there was a half and a half on both sides, so I'll get rid of that. And we're looking for the muzzle speed, so we're looking for v final. So v final squared would be equal to k divided by m times x initial squared, where v final is really equal to the root of the spring constant multiplied by the mass and then multiplied by x initial. Now x initial, by the way, is just the magnitude of it. So you're not going to put in negative 0.08 centimeters. You're just going to be thinking this all in terms of magnitude. So now you can substitute in here. Your spring constant is 400 newtons per meter. The mass of the dart is 20 grams, but you need to convert that 20 grams, by the way, into kilograms. So remember, 1 kilogram, there's 1,000 grams in it. So that's 0.02 kilograms for that mass. Okay, and then we're going to multiply this by the displacement from equilibrium, which is 0.08 meters. So this is going to give you a final answer of 11 meters per second. And hence, this is the muzzle velocity. Notice some things, by the way, with this. You can see that the velocity is directly proportional to the displacement. So if we were to move the dart back, say only 4 centimeters back instead of 8 centimeters, so half of the distance, then what would happen to our velocity? Oh yeah, our velocity would be only half of this amount. Or what would happen if you change the spring constant? If you were to double this, the speed is proportional to the square root of the spring constant. So if you were to, say, quadruple that spring constant, then your speed would double. So it's important to kind of come up to this point right here and see the relationship between all the variables. All right, that's it for this problem.